The width of the depletion layer of the junction. There is a formula for depletion layer of the junction which is given by W is equals to root of 2 epsilon naught VBI minus V divided by Q into N. W is the width of the depletion layer of the junction, where epsilon is the permittivity of the semiconductor, VIB is the built-in potential, V is the reverse bias potential, Q is the charge, and N is the effective doping concentration, where N is given by Na into Nd divided by Na plus Nd. Na is the acceptor concentration and Nd is the donor concentration. See, if we look at the options, the first option, the width of the depletion layer of the junction is independent of the applied voltage. See, here we can see that it is dependent on the applied voltage. Decrease with the light doping. That means light doping means smaller N value. If N is small, W would increase. So it increases with the light, actually it increases with the light doping, increases with the reverse bias voltage. V is the reverse bias voltage. So if as V increases, width also increases. So option C is correct because it increases with the reverse bias voltage, increases with the heavy doping. Heavy doping means larger N value. If N is large, that means W will decrease. So option C is correct. The band gap of the semiconducting material used to make an LED is 1.43 electron volt. What will be the maximum wavelength of the radiation emitted by this LED in micrometer? I have given energy value, energy band gap value, that is 1.43. Energy band gap value is 1.43 electron volt. What will be the maximum wavelength of the radiation? That means they have asked radiation in micrometer. We have to find lambda in micrometer. So we know the formula, E is equals to hc by lambda. E is 1.43 electron volt. hc, during calculation we can simplify it and write the value as 1240 divided by lambda. Lambda we will get in nanometer. If we use 1240, then lambda we will get in nanometer. Then lambda in nanometer is equals to 1240 divided by 1.43, which is equals to 867.13 nanometer. Now we have to find lambda in micrometer. So lambda in micrometer is nothing but 867.13. Nanometer is 10⁻⁻9 meters. So we need in micrometer means we need it in 10⁻⁻6. So 9 minus 6 is 10⁻⁻3 into 867.13. So it would be 0.86 micrometer. So lambda in micrometer is 0.86 or 8.6 into 10⁻⁻1 micrometer. 8.6 into 10⁻⁻1 micrometer. Due to breaking of the periodicity at the surface of the semiconductor. If we disrupt the periodicity on the surface of the semiconductor, that means bonds are broken. See, if we disrupt the periodicity at the surface of the semiconductor, what happens? The bonds are broken. These broken bonds are known as dangling bonds. These dangling bonds create energy levels inside the band gap. What happens when we disrupt the periodicity or when we break the periodicity at the surface of the semiconductor? The bonds are broken. These bonds are known as dangling bonds. These dangling bonds create energy levels inside the band gap. That means if this is a conduction band, and this is valence band, this is known as energy gap. Due to disruption of the periodicity, the dangling bonds are created, which creates an energy level inside the band gap. So the energy levels are created inside the band gap. These energy levels are known as surface states. These energy levels are known as surface states. So due to breaking of the periodicity at the surface of the semiconductor, impurity states are created in the band gap. No, impurity states are created when we dope the semiconductor. Doping of the semiconductor takes place. Doping means adding atoms into the semiconductor intentionally. Breaking of the periodicity doesn't dope the material. Surface states are created in the band gap. Yes, surface states are created inside the band gap when breaking of the periodicity at the surface of the semiconductor takes place. Extended states are created in the band gap. No, extended states belong to bulk bands, not the localized surface. So option C is correct. In an indirect band gap semiconductor, for an electron to get excited to the conduction band, only when. Let us recall some basic concepts about semiconductor. In semiconductor, we know that there are two types of bands: conduction band and valence band. This is conduction band and this is valence band. The electrons are mostly present in the valence band. These electrons can jump into conduction band if they gain enough energy. This energy difference is called the band gap or energy band gap. This is called energy band gap. In a direct band gap semiconductor, example is gallium arsenide. The conduction band and valence band, this is conduction band and this is valence band. The top of the valence band and the bottom of the conduction band, they occur in the same momenta, which means that the electron can jump from valence band to the conduction band straight up by absorbing only a photon of energy equal or to higher than the energy band gap. In indirect band gap semiconductor, for example silicon, the conduction band and valence band are not present in the same momenta. They are present at the different momenta. That means valence band is here and conduction band is here. This is known as indirect band gap semiconductor. In direct band gap semiconductor, both valence band and conduction band, they are present in the same momenta. Here the electrons cannot jump from valence band to conduction band only by absorbing photon. Here it can directly jump up to the conduction band just by absorbing photon. Here it cannot jump just by absorbing photon. It needs photon plus phonon. A photon alone can't provide the momentum needed for the electron to jump. We need a phonon, which is basically a vibration of the crystal lattice, to help conserve the momentum. So in the indirect band gap semiconductor, the electron needs both photon and phonon for momentum to jump from valence band to the conduction band. So for direct band gap semiconductor, we need only photon, and for indirect band gap semiconductor, we need photon plus phonon. If you look at the options, in an indirect band gap semiconductor, for an electron to get excited to the conduction band, that means from valence band to conduction band, a photon of energy higher than the band gap is required. No, this is required in direct band gap semiconductor. A phonon is required. No. A photon of energy higher than the band gap and the phonon are required. Yes, in indirect band gap semiconductor, a photon plus phonon is required. A photon, phonon and temperature are required. Temperature is not the strict requirement. In an allowed band of semiconductors, the effective mass of the electron is infinite. Okay. Effective mass is finite at the bottom of the conduction band and top of the valence band, but in the middle it is infinite. At the bottom of the energy band, no. At the top of the energy band, no. In the middle of the energy band, yes. It is infinite at the middle of the energy band. At any temperature, the probability of occupation of the electron at the Fermi energy is The probability that an energy level E is occupied by the electron is given by Fermi Dirac distribution, which is given by f of E is equals to 1 divided by 1 plus e to the power of E minus EF divided by kBT. This is the Fermi Dirac distribution. At any temperature, the probability of the occupation of the electron at Fermi energy means E is equals to EF. Then f of E is equals to 1 divided by 1 plus e to the power of EF minus EF divided by kBT, which is equals to 1 divided by 1 plus e to the power of 0. E to the power of 0 is 1. That means f of E, that is probability f of E is equals to 1 divided by 1 plus 1, which is equals to 1 by 2. So the probability of the occupation of the electron at the Fermi energy is 1 by 2. A small concentration of the minority carriers are injected into the homogeneous semiconductor crystal at one point. The electric field of 25 volt per centimeter is applied across the crystal, and this moves the minority carriers a distance by 3 centimeter in 10 microseconds. The mobility is given by, okay, so what they have given electric field E is equals to 25 volt per centimeter, and they have given distance D is equals to 3 centimeter and time 10 microsecond, and they have asked mobility mu. We know the formula for drift velocity Vd is equals to mu into E, where mu is the mobility and E is the electric field. Then mobility is equals to drift velocity by electric field. We know the formula for velocity is nothing but distance upon time. So distance is 3 centimeter, that is 3 into 10 power minus 2 meter, divided by time is 10 microsecond, that is 10 into 10 power minus 6 second. So it is nothing but 3 into 10 power 5. Then mobility is equals to velocity 3 into 10 power 5 divided by electric field is 25. This is 10 power 5, electric field is 25. 3 into 10 power 5 we can write this as 100 into 10 cube. 3 plus 2 is 5, so divided by 25 4s are 100, then 4 3s are 12 into 10 power 3, which is nothing but 12,000 centimeter square per volt second. 12,000 centimeter square per volt second. The Fermi level of an n-type semiconductor is, in n-type semiconductor we know that electrons are more, that means the Fermi levels are closer to the conduction band. Fermi level is close to the conduction band for n-type semiconductor. For p-type semiconductor, Fermi level is close to the valence band. The rest questions I will cover it in the next video.